Hello, my friends. As you no doubt have noticed, we're doing something a little strange today. So I've taken off and I'm at Kingston Middle School and I'm teaching Miss Manugit's classes this afternoon. And Miss Manugit, and Carla, if I've just mispronounced your name twice, I apologize. But Miss Manugit came up here to teach you guys for a day. And the reason we did this is you guys did such a fantastic job on that MSP last year that Mr. Gore and Miss Manugit wanted to come up and just, say thank you and what an awesome bunch of guys and gals you are. And I couldn't do anything other than just echo that. You guys are just a fantastic class. So today though we need to push forward. And right now we're kind of floundering with this idea of balanced forces, unbalanced forces, and acceleration. And today we're going to try and really get it squared away in our heads. So what we're going to do is just do a 4 or 5 minute review here at the very beginning. Just do some notes in our lab notebook. And then you're going to work through an activity with Ms. Manugit where you're going to get lots of feedback using the whiteboards about whether you have these ideas down or not. And at the end of the period, maybe the last 5 or 10 minutes, you're going to take another snapshot quiz to kind of see where we end up at the end of the period. All right, so that's the plan for the day. Let's get to it. So do me a favor and open up your lab notebook to that next open page. And let's just do a really quick review here, a quick rundown of what we've been talking about in terms of motion. So there's actually only 5 different things you can do when you're in motion. So I'm going to put up here, I'm going to say here, this is a review of motion and forces. Actually, we're going to talk about both. So there's only like 5 different things you can do for motion. In terms of motion, you can describe all motion with 5 different phrases. You are either at rest, which means you're not moving, right? Or you're moving at a constant velocity. And if there's anybody who's asking the question of like, should we write this down? The answer is yes, you should. So those 2 are 2. There's 3 more, and you can get all motion described. And that is, you could be speeding up. And I think you know the other 2, slowing down, or turning. All right, awesome. And of course, we've called these 3 together over and over again. These represent acceleration. So anytime you're doing any of these 3 things, you're accelerating. These 2 things represent not accelerating, right? There are only 2 ways to not accelerate. It's either to not move or to move at a constant velocity. And there's only 3 ways to accelerate: speed up, slow down, turn. If you do any of these 3, you are accelerating. If you either of those 2, you're not accelerating. And then the next step was to attach this to the forces causing it, right? So here we said that the forces are unbalanced. And here we said the forces are balanced. Or they're 0. There's like no force, right? 2 options here. So either balanced or no forces. And when it's balanced, it's the same in both directions. It's as if there's no forces at all. They cancel each other out. Awesome. So we have these 2 situations. These 2 are going to guide us all day today, and we'll leave them on the screen for you. This is key. Like if you know this information, you get it all really in your head, you can predict all kinds of stuff that happens in the world. All right. Let's do a quick example for a force diagram that we're all on the same page. So I'm going to draw a quick car here, and I want you to draw it as well. And I didn't want the wheels to touch the ground. That would help. And I'm just going to draw, I don't know, a little like, ooh. Hey, when you're drawing a car, I learned when I'm drawing a car that you make the nose a little bit longer than the back, and it looks like a car instantaneously. So if you're not good at drawing cars, that's a good little tip. So just make that nose long and the back short, and then give it 2 tires. Now the first force we have on this car, we make sure to get this obvious force, this one of this right here, pulling down, and that's the force of the earth. Now remember, we label our forces with the object causing the force, and this might commonly be called gravity, right? So we commonly call this force gravity, but it's really the whole earth pulling you down. And then we look up here and we say, okay, is this car accelerating downward or upward? Is it speeding up, slowing down, or turning up or down? And hopefully we all realize that the car isn't doing that because it's on a road. So the forces must be balanced, which means we're not accelerating and the forces are balanced. So the force that balances this downward pull of the earth is the upward push of the road on the tires. And I'm going to try and make these 2 arrows exact same to show that they are balanced. I'm going to put here, this is the force of the road pushing up. So far so good. So these 2 forces balance, they cancel out. You don't speed up, slow down, or turn in the vertical direction. So you're not speeding up upwards, right? If you could imagine putting this car into a trampoline and then pulling down from the bottom so the trampoline is super duper stretched and then letting go, well, this upward force would be greater and you would just fling the car off the trampoline, right? So that's how that one works. Okay, so what's next? We need to know something more about the car. Let's say the car is moving at a constant 55 miles per hour. Now, Newton's laws tell us that an object in motion should just stay in motion. So this car should just be able to zoom right along without any extra force added to it. The only problem with that reasoning is that there is some force acting on this. As you move 55 miles an hour, if you don't believe me, try this next time you're driving in a car. Stick your hand out the window, and even better yet, get like a big sheet of plywood and stick that out the window. No, don't do that. I'm just kidding. That'll rip your arms off, right? So there's this huge force of air that pushes back on the car this way. Now there's also friction with the tires in the road and inside the car, and so there's all these other little frictional forces, but the main one is going to be the air pushing back. So we're going to put a force here pushing back. This is all those frictional forces. And I'm going to do something weird here. I'm going to label this one F sub friction. Now, if I was being super careful here, I would label a bunch of different forces, like force of the road pushing back, that's one friction, force of the air is another friction. But I'm going to put all those frictional forces together into one force and call it force friction. And this would be the only time, I think, that we use a force without the object causing it, because there is no object as friction. Now, to be moving at a constant 55 miles an hour means, right here, moving at a constant velocity, I'm not accelerating, therefore the forces must be balanced. And this is why it requires you to keep your foot on the gas. If you don't push forward, like if your car doesn't push forward as hard as the air and everything is pushing back, you will slow down. It's got to push the exact same. Now, what causes this forward force? You might initially think, well, it's the engine or the tire. But remember, the tire pushes the road backwards, and it's the road that pushes the car forward. So this is actually the force of the road. So it's kind of cool to think that the road does 2 things. It pushes up on the car here and forward on the car here. To drive a car, the road is like super duper important, which makes sense. I mean, you toss a car out of an airplane, you can't just drive it around in the air. You need something like a road. And if you ever do that, don't worry, the road's coming. It's coming really quickly. It'll be there in a second. So far so great. So we have this balanced forces, this force equal to this one equal to this one. It's as if there's no forces acting on it. So an object in motion will just stay in motion. It'll stay at a constant 55 miles per hour. All right, so this is a good force diagram. You're going to be using those forces during the activity today. I'll walk you through that in just a second. All right, so here's what you need to do now. You're going to be drawing forest diagrams similar to one we just drew together. You're going to be drawing those in a bunch of different situations for a car. And what we're going to do is Miss Manuga is going to take you through this activity. And you need one whiteboard and a marker for every 2 people. Let's take a second and get that done real quick. Everybody go grab a whiteboard and marker. You know where they are. All right. I'm assuming those 3 seconds were plenty of time for you to grab a marker. If not, let's hit the pause button and wait until we get them. Now, what I have arranged for you today is you're going to go through a series of scenarios with a car driving on a road, and you're going to be drawing the forest diagram for it. But before you draw the forest diagram on your paper, you're going to actually draw it on the whiteboard, and then you're going to hold it up for Miss Manuga, and she's going to give you a thumbs up, a thumb sideways, thumb down, give you some feedback on it, make sure that you have really good forest diagrams, and then once you're good, then you'll copy it down. And here's how the drawing works. So you'll take turns every picture. One person will have the marker, and that person does not draw what they want. They're being told what to draw by the other person. So you've got to work together. So whoever wants to start out with the marker first is not the person answering the question. They're the person following the instructions of the other person. So we've got to work together on this. And then for the next drawing, you'll switch roles, and the next person will then be the describer, and the other person will be the drawer. And that doesn't mean if you're the drawer or describer, you can help the other person out. So if you're the drawer and they say draw something, you're like, wait, but you think that's right? Let's think about this way. That's totally okay. And then we're going to get them all approved and then get them into our activity for today. All right, any questions for me? Awesome. If we haven't already, this is the point where we need to pass out the activity and make sure we all get it taped into our lab notebook. That should take no more than 2 or 3 minutes. At the end of the period, we're going to take another snapshot quiz to see where we are in our learning. All right, you guys are awesome. Ms. Manuga's in charge. If we want to leave this up, it might be nice to have this summary on the screen, even though it's in your lab notebook as well. And we will see you tomorrow, my friends. Have a great day and enjoy your winter break.